Hi there, welcome back to this channel. In this video we are going to be considering the Brewster's law. I'm very sorry it took me time to release this video. I've been away for some time. So if it's your first time, do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. All right, let's talk about the Brewster's law. In order to understand the Brewster's law, you must, of course, already know about polarization. So now polarization is a concept that explains the motion or orientation of the electric field, the electric field in an electromagnetic wave. Okay, so usually when we make electromagnetic wave first is a transverse wave. So, and that is why it is polarizable. So only transverse waves can be polarized. I've explained that in previous videos. Do well to see those videos. All right. So if transverse waves are the only waves that can be polarized, not longitudinal, then what does polarization mean? Polarization means that you already know that transverse waves are waves that travel in a direction that is perpendicular to the direction of their propagation. So if they are traveling like this, the oscillations of the wave might be going up and down and back and forth, and both of them, and the waves will be moving like this. Is that okay? And an example is the electromagnetic wave, which is transverse. So light wave, which is one of the electromagnetic wave spectrum, is one in the electromagnetic wave spectrum or EM wave spectrum, is a transverse wave and it can be polarized. And what that means is that the electric field is going to be made to pass a particular opening. It's going not to pass an opening. It's going to be made to travel in one direction rather, only in one direction. So what we use in polarizing is called a polaroid. A polaroid, and an example is the tourmaline. So what the polaroid does is that it allows the light wave that was oscillating in both directions before, to make it pass so that only one direction is going out of the polaroid, or this oscillation is going out of the polaroid, depending on the orientation of the polaroid. Okay, so now what do we need to understand about polaroid? About Brewster's law. Now, one of the methods of polarization is using polaroid. Okay, there are other methods of polarization, and one of them is polarization by reflection and polarization by refraction. So we are going to be seeing polarization by reflection. Okay, so light wave can be polarized by reflection. So usually when we tell you that when the ray of light is incident on a surface, okay, let me draw my normal, we know that the angle of incidence is going to be equal to the angle of reflection, right? It's going to be equal to the angle of reflection. But one thing that you should also know is that this angle of reflection here will not contain all the property of the wave that was incident here. Will not contain everything in, it's not all the wave that perfectly got incident here. Do you understand? Even though the angle is the same. Okay? Now, some of the part of this wave would have been polarized. So that if the wave that was traveling here has oscillations in this direction, the wave that traveled down oscillated in this direction. And I hope you understand what I mean by those crosses. A wave will be going up and down like this, and that will be going into and out of the board like this. Into and out of the board. Okay, so one wave is going into and out of the board, the other is going up and down. So that's what I'm showing you there. Okay, I'm representing it with those crosses. All right, now if we have a wave like this, by the time this wave strikes this surface, okay, now let me represent these ones. Okay, then of course it gets here. Now these ones that are going up in the y-axis, let's represent them with lines. Then the ones that are in x-axis in this direction, let's represent them with dots or star. So by the time this wave is reflected, remember this is the reflected ray. the reflected ray. I just said now that this wave will be polarized partially. Partially, okay? There's going to be a point where we will have full polarization, and I'm going to explain that. And that's where the Brewster's law comes in. So by the time this wave gets reflected, what you will see is that this wave that came like this, perfect like this, will only have one component. One component. Only one component. Now, this is when there is actual perfect polarization or full polarization, that's the word. But in this case, because in case of partial polarization, you still see some, I'm representing this with a star now, this guy. Okay, let me just draw it there. You still see some, in some places, the other wave that is traveling perpendicular in the z-axis is still going to appear. Do you understand? So if this was x-axis, this is y-axis, this will be our z-axis. This will be our z-axis. Is that clear? So some waves that are still traveling in the z-axis will still appear in some places. In that case, we say it is partial polarization. Partially polarized. Okay? But if it doesn't have any of the oscillations in the z-axis any longer, then we say it has undergone full polarization. Now, how does it undergo full polarization? Experimentally, it has been shown that as you increase the angle of incidence, you keep increasing and increasing, as the rays are being reflected, they are being reflected as you are increasing this one, as they are being reflected, a time is going to come where, as they are being reflected first, know that they will be polarized. Do you understand? They will be polarized partially and partially and partially. But we are going to get to a particular angle that we call angle theta. We actually call it angle theta B, that is Brewster's angle, where this polarizing angle will be perfect. Do you understand? That is, this ray will be perfectly polarized and will not have anyone in the z-axis again. All of the waves that are going to be shown here are going to be perfectly polarized or fully polarized. So this will be said to be fully polarized. Fully polarized. But before that point, the polarization will not be full, it will be partial. Now, if you go beyond that angle again, the polarization will become partial again. So it's at a particular angle. Do you understand? So remember also that this principle actually works for transparent surfaces. Do you understand? Such as transparent surfaces that can also allow for refraction, such as air, such as glass, dielectrics like glass. These are the surfaces that can, prove this refraction, surface that can refract. So you also know that since this surface can refract, that is, it can make the light to pass from this medium to another medium, let's call this air, and let's call this second one water or glass. So this place is glass, this place is air. So air that is coming here, some of it will be reflected, and of course by reflection, once we get to that angle, the Brewster's angle, as I called it, Brewster's angle, there's going to be full polarization of the wave. But also take note that this wave is also going to be refracted. This wave is going to be refracted. Okay? It's going to be refracted. It's going to be refracted. I didn't quite draw that very well. Okay? No, refraction should not, it should bend, okay? So experimentally, it has been seen that at this Brewster's angle, where the angle of reflection is going to reflect, the angle of reflection will consist of a fully polarized wave. At that angle, at that Brewster's angle, the angle between the reflected ray and the refracted ray refracted ray is called, is 90 degrees. Is exactly 90 degrees. That is, at this angle, this Brewster's angle, where there is full polarization of the reflected ray, the angle between the reflected ray and the refracted ray is 90 degrees. Okay, so let's call this theta r for refraction, for angle of refraction. Let's call if this is theta r, remember that initially from here to here is also 90 degrees. So it means that from here to here will be 90 minus theta r. Does that make sense? Then it also means that here, this angle here, if from here to here is 90 degrees, and this place alone is 90 minus theta, it means that for this place to be equal to 90, then it means this place needs theta r. Does that make sense? And if that is theta r, then it also means that this place too must be 90 minus theta r. I hope I didn't confuse you. Angle of refraction. So from here, from this place to this place, we have 90 degrees, right? So this will be 90 minus theta, okay? If that's the case, from here to here is another 90 degrees, right? So if this is 90 minus theta, then this if it's 90 minus theta, then this minus theta. This must be theta rather. If this is 90 minus theta, this must be theta minus r. This must be theta r, okay? Then if this is theta r, then this must be 90 minus theta, because we have another 90 degrees here. I hope that is clear now, okay? Now, and remember that Snell's law states that the angle of, Snell's law states that the angle of refraction, not Snell's law, the law of reflection, exactly, says that the angle of incidence is equal to the angle of reflection. Therefore, if that be the case, since theta I is equal to theta r, that means that theta I must be equal to this 90 minus theta r. Keep in mind, this my r is for refraction. Exactly, it's for refraction. Okay? So if that be the case mathematically, remember also that Snell's law, let me bring that here. Snell's law states that the ratio, that the refractive index of two surfaces is equal to the ratio of the sine of angle of incidence to the sine of angle of refraction. Okay? And it says that the ratio of this sine of this, the ratio of the sine of these angles is a constant for any given pair of medium, right? So that we will say that this is equal to n2 over n1. Does this make sense? Okay. Now using this equation here, then we have that you should already know this, exactly. So we have that mu will be equal to sine I over, now, or sine theta I. Let me use theta I to represent angle of incidence. Then over sine theta r. Remember, from here we can therefore say that theta r will be equal to 90 minus theta I. Okay? So if this is true, then it means that if I have sine theta r, remember that in this trigonometric relationship, you know, we normally say that the sine of an angle is cos 90 minus that angle. Does that make sense to you? The sine of an angle is equal to cos 90 minus that angle. So that if I have sine of theta r here, it means it to be cos 90 minus theta r. Is this clear? Then already we know that theta r is 90 minus theta I, right? Okay? So I can therefore say that I can substitute into this equation, if that makes sense to you. So sine theta r will be equal to, keep in mind that this is refraction, cos 90 minus theta r is 90 minus theta I. So that will be minus 90 minus theta I, okay? So if this is the case, then we'll have that sine theta r is equal to cos 90 minus 90 plus theta I. So here, because they are all in degrees, then we have 90 minus 90 is what? 0. So we have sine theta r is equal to cos theta I. Does this make sense? So I can bring that into this equation and say that mu will become sine theta I over cos theta I. Okay? So if this makes sense, then it means that since we remember that sine over cos is tangent, then it means that mu is equal to what? Tangent of theta I. So this is the Brewster's law. I'm going to explain again in detail so that you understand what I just said. But mathematically, this is Brewster's law. Or you can replace this mu by this so that we have tan theta I will be equal to n2 over n1. Okay? So that n1 tan theta I is equal to n2. Alright? And just begin to derive your equations from there. If this is equation 1, this is equation 2. Okay, so that's the mathematical proof for the Brewster's law. Now, what I said about the Brewster's law is that at the Brewster's angle, the angle of reflection and the angle of refraction are at 90 degrees to each other. They are at 90 degrees to each other. Okay? So that's what was experimentally discovered. Okay? So by the time, and it is at that point where there is full polarization by reflection. Is that clear? There is full polarization by reflection. Alright, that will be it for Brewster's law. Do well to subscribe to the channel and click the bell notification to get notified whenever I drop a new video. God bless you.